And welcome. Have you ever just stopped and looked around? I mean, really looked. If you do, you'll notice that everything is constantly changing. The ice melting in your drink, the food cooking on the stove, our entire world is in a state of, well, constant transformation. Today, we're going to pull back the curtain and decode the science behind these everyday moments. Let's kick things off with a few examples you'll definitely recognize. First up, something super simple: slicing a loaf of bread. Sure, the shape and the size of the slices are different from the whole loaf, but is the bread itself any different? Nope, it's still bread. Tuck that thought away for a second. Okay, now what about boiling an egg? You start with that gooey, liquidy stuff inside, and you end up with something solid and white and yellow. Talk about a dramatic change, right? And for our last little example, let's look at something we've all seen a million times: liquid water freezing into a solid block of ice. It goes from being totally clear and flowy to hard and frosty. Its whole look and feel has changed. So, here's the $1,000,000 question. All three of these are definitely changes, but they are not all the same kind of change. One of these things is not like the others. Any ideas which one it is? Well, that's exactly what we're about to figure out. To crack this code, we need to understand the two main categories that all changes fall into. So, let's dive into section 1 and start with the first type: physical changes. A physical change is really all about appearances. You can think of it like a substance just changing its outfit. It might look different, changing its shape, its size, or even its state, from a solid to a liquid to a gas, but deep down, underneath it all, it's still the exact same stuff. No new substance gets created. That's the key. And this is the perfect way to picture it. You've got liquid water and you've got solid ice. They look and feel completely different, right? But if you could zoom all the way into the molecular level, you'd see they are 100% identical. Both are just H2O. The molecules haven't changed, they've just kind of rearranged themselves. That is the very essence of a physical change. So, how do you spot a physical change out in the wild? Well, here are the telltale signs. The original stuff keeps its identity. The change is usually temporary or reversible, and only those physical properties, like shape and size, are affected. But the big one, the most crucial point to remember, is the last one. If no new substance has been made, you are looking at a physical change. Period. Just think about it this way. If you rip a piece of paper into 100 little bits, what do you have? 100 little bits of paper. The substance itself is totally unchanged. Or if you stir sugar into your coffee, the sugar crystals seem to disappear, but they're still there, just mixed in. You could even get them back if you boiled off the coffee. It's a physical change. But let's circle back to that bread. When you toast it, you can't untoast it, right? The color, the smell, the taste, everything is different. Something way more permanent happened there. And that brings us to our second section, and what I like to call the real magic of chemistry: chemical changes. A chemical change, or what scientists call a chemical reaction. Now, this is a total transformation. We're not just changing outfits anymore, we are changing our very identity. A chemical change creates an entirely new substance, something that wasn't there before, with a whole new set of properties. Let's go back to that toast. When you pop that bread in the toaster, the heat causes the sugars and amino acids in the bread to go through this super complex reaction. The result isn't just hot bread. It's toast, a totally new substance with a different chemical makeup. You literally started with one thing and ended up with something else entirely. And this shows you what's happening on that teeny tiny molecular level. See, we start with one thing: hydrogen peroxide, or H2O2. But when a chemical change happens, its molecules are literally broken apart and then put back together in a new way. And the result? Two brand new substances are formed: plain old water, H2O, and oxygen gas, O2. That is a chemical change in action. Burning something is another fantastic example. When you light a match, the wood is reacting with oxygen from the air, and it's transformed into totally new things: ash, smoke, different gases. You can't just scoop up all that ash and smoke and remake the match. It's impossible. A new substance was created, and that change is permanent. Okay, so we've got these two different types of change. How can we tell them apart? Well, there's a really handy mental shortcut we can use. But just a heads up, it does come with a small catch. Let's call it the reversibility test. It's actually pretty simple. A reversible change is one you can undo. You can melt an ice cube into water, and then you can pop that water right back in the freezer and turn it back into an ice cube. That usually points to a physical change. But an irreversible change, well, that's a one-way street. You can't unfry an egg, and that almost always signals a chemical change. Now, remember that catch I mentioned? Here it is. While the reversibility test is a great rule of thumb, it's not 100% foolproof. As this quote here points out, some physical changes are actually irreversible. I mean, you can't untear a piece of paper, but it's still just paper, right? No new substance was formed. And this is the perfect illustration of that tricky exception. Cracking an egg is a physical change. You've changed its shape, its structure, but the shell is still shell, and the yolk is still yolk. Nothing new is made. But is it reversible? No way. You are not putting that Humpty Dumpty back together again. All right, we've explored the definitions, we've looked at examples, we've even tackled the tricky exceptions. So for our final section, let's just put it all together. Here is your definitive guide for spotting the difference every single time. This chart right here is your ultimate cheat sheet. But I want you to focus on that very first row. It's the most important question to ask, always. Was a new substance created? If the answer is no, you are looking at a physical change, where the identity of the stuff is maintained. If the answer is yes, then it's a chemical change, and a whole new identity is formed. Everything else, like whether it's reversible or not, really just follows from that one key difference. So the next time you cook dinner, or light a candle, or even just take a breath, you'll see the world just a little bit differently. You'll see this constant, invisible dance of molecules, rearranging themselves in physical changes and totally transforming in chemical ones. Now that you know the secret code, what other changes can you spot happening right under your